pi by 2, 0. So you can see where we're going with this. Then you've got a minimum negative times a minimum negative, which will be a maximum positive, and that's at 3 pi by 2. And then again a 0 times a 0 at the end of the sine curve to give you 2 pi. And that's why you'll have two peaks within one sine cycle, one 360 degree or 2 pi radians cycle. So that's just something interesting, something useful to note and reflect on with that. Now, this is where we start to get to the idea of RMS, or a root mean square, or an average value. It's actually not that helpful to have these peak values. So peak power, peak voltage, peak current in the above graph. What is helpful is to have a constant value that is roughly a constant power delivery for us. And in terms of this graph, we could just chop that whole top section off and plop it into the gap under here, and do the same for there, and just keep doing that. And we would find that our peak power, our average power, which is our DC equivalent, is actually just your P max, your maximum power, divided by 2. And that's a consequence of the P equals I times V thing, and it makes it kind of nice and easy for us. I should say as well, why we're doing this is your meters don't read nicely. If you're trying to read an AC voltage and an AC current using like a DC meter, it'll give you a 0 reading, because it has an equal amount of time above in the positive and below in the negative. So they'll average out to 0. That's like up here, your sine curve averages out to 0, just a nice 0, because those kind of equal and opposite and cancel each other out. So we want to have some sort of DC equivalent, because you can't actually have a negative power delivery, can you, anyway? Because that's changing energy over time, and if you're doing work, if you're changing energy in its form, it has to change. It has to be an actual positive power going on, rate of change of energy. Anyway, getting back to the point, we actually have, I'm going to cut straight to the end, then I'll show you how we derive it. We have what we call an RMS value. IRMS is the DC equivalent for an AC, and that is your I max divided by the square root of 2. And you get the same thing with voltage. VRMS, our DC equivalent, is your Vmax divided by square root of 2. There's a couple of interesting things, that the area under a sine curve, under one hump of a sine curve, is 2. And if you imagine that there's a sort of a... 1 over the square root of 2 is 0.7, roughly. And the length of your sine curve, this is just interest kind of stuff, the length of your sine curve for one hump is 3.1415, about 3. Okay, and the your 1 over square root of 2 is about 0.7. If you were to take 0.7 here times by 3, you would find the average value there. The average, and put it all positive, of course, will just give you a nice average value. So that's just something interesting. You can explore the calculus of it. You can explore integrals, which is how you find the area under a sine curve. But I'm not going to get into that. I'm going to show you how we derive these IRMS things. I'll try and be quick about it, because otherwise the video will be too long. Might have to split it into two. I think I said it would anyway. So anyway, your average power, which is what we're trying to find, this DC equivalent, is going to be I RMS times by V RMS. Okay, because those are what we've defined as our DC equivalents, and they equal P max over 2, and P max is going to be I max times V max, and we're still divided by 2. We can use our, if we get rid of that now, and we're just dealing with the IRMS, VRMS over I max over V max, we can do some substitutions which will cancel out some things nicely for us. And what we're going to do is we'll just do one of them and you can go through and do the other one in your own time. Remember, P equals I squared R. So we're going to substitute I squared R for I RMS and VRMS. VRMS, well, I RMS times VRMS is equal to P RMS, or the average P. So we're just going to go take the left hand side and make that I RMS squared times R, the resistance of the load, instead of doing I times V, so it equals the same thing. Okay, and then on the right hand side we're going to use the same formula, but this time instead of applying it to the RMS, we're going to use it applied to the max. So I RMS squared R equals I max squared R, and it's still divided by 2 because that I max squared R equals the power, which equals I max V max. Anyway, you can see where this is going. We're going to cancel out the R's, and if we take the square root of the left hand side and the right hand side, it's going to get rid of the square root there, get rid of the square root there, and we're left with I RMS equals I max divided by square root of 2, which is what we're aiming for all along. And I just wanted to give you one other thing here. This average PAV, or the power, not the PAV actually, sorry, just Pmax. Pmax is gives us a nice equation which you need to see just so you're aware that it exists. Pmax is going to be Imax times Vmax. Oh, in fact, scrap that. Just the power at any one point in time is going to be I times V, as we know, but our I varies. It goes I max times sine omega t, and our our V at any one point in time, sometimes I draw random lines just for fun, our V is V max sine omega t, and it looks awkward when you start multiplying signs and that, but you end up with I max V max, I should write equals, and then the sine squared omega t. So that's just for the power at any one point in time if you happen to have to work with those parts of the equations, the AC equations rather than DC equivalents. Huge long video, that's plenty for now, and that's your introduction to AC electricity.